two reasons really why I think it's a very good occasion that we're here tonight. On this day, 1660, there were 12 learned gentlemen, as it was then, came together to form an organisation to look at a college of physics and mathematics in experiment and trial, to look at things that had a real impact on society. Can you guess what that organisation was? Royal Society. So the Royal Society was formed on this day in 1660 with that absolute ambition to come together to talk about physics and maths, as it said, on things that was really instrumental to society. And I think we might argue a bit about timescales in exploiting technologies like graphene, but it'd be hard to say that it's not going to have an enormous impact on all of our lives, graphene and 2D materials going forward. The second reason is that this is really the end, at least for the time being, of a culmination of events we've been running around graphene and 2D materials to bring together the academic community, industry, policymakers, to look at how the UK can begin to exploit some of this technology based on the really groundbreaking research that has been led by people like Konstantin and the team working on that in the UK. So says if you look at the biog, I won't go through the whole biog, but Konstantin was born in Nizhny Tagil, and I apologise. I'm sure that's not recognisable to any Russian speakers as a pronunciation. But so I did the first thing that all self-respecting people do, so I Wikipedia'd it to find out more. And interestingly, so it's in the Urals, close to the border between Asia and Europe. But it has a long tradition in materials, metals, malachite, monocrystal structures. So I don't know whether you could argue that it's actually in your blood, but at least there's some destiny connection there that you are going to be working in some of these areas. Come in. So, please do. So with his colleague and longtime collaborator, Andrei Geim, he became one of only 195 people to win the Nobel Prize for his work on graphene. And he did that at the age of 36. So, sorry, I apologize to give your age away, but I'm now looking at the young members of our audience, the young scientists, and saying, get a move on. It's too late for some of us, but you need to get a move on. So it's not often that we get the opportunity to hear such an eminent scientist speak, and for me it's a real privilege to be able to introduce him to you. So, ladies and gentlemen, Professor Sir Konstantin Novoselov, and he's going to talk to us about graphene materials in the Flatland. Konstantin, over to you.
Good afternoon, everybody. It's a great pleasure to be here. Thank you so much for this invitation. And so, indeed, we'll try to go through the properties of graphene and why so many people are excited about it. But also, I will try to go a little bit beyond that and show you what kind of opportunities it gives to us, and also what kind of further research is promoted. Let me start with a story, though. About a couple of years ago, I think, the present government announced the creation of the UK National Graphene Institute. So that's how it's supposed to look like in about a year time. That's how it looked just a few months ago when we were doing archaeological survey, and we were quite pleased to discover a few rows of old workers' houses, 1719, 1840, and on top of that we also dug out quite a large building which turned out to be the so-called Albert Clubhouse. And in principle, nobody would remember about this Albert Clubhouse, but this gentleman was its member, and that's why we can find some information about it. Any guess? A gentleman with a beard, 1820, Manchester, Frederick Engels. And so then the story is that we have to every single building on the campus is supposed to be named after a famous Mancunian. So physics, where I work, is Schuster Building, Maths and astronomy is Turing Building, and so on. So of course, we rushed immediately, or I rushed to our vice president asking, can we name the Graphite building the Engels Building? And surprise, surprise, the response from the present government was that basically we give you money to do research, not to explore your communist past. So, however, since the official opening of the building is still 2015, although we hope to start populating it next year, so the general election is still around the corner. So who knows, with the Labour government, we might be allowed to call it the Engels Building, especially because, of course, Engels was advocating for new technologies to promote to promote the technological progress, although he saw it as a threat for common folks, like common workers. But okay, alas, we know that it has to be done. So there is some connection there. Now let's go to graphene, and we will talk still about the technological applications of this material a little bit later. So let me start with really the basics. Let me start with the introduction. What is graphene? And the best way to introduce it, the way usually people introduce it, is to asking the audience to think about different forms of carbon in terms of dimensionality. So we know very well the three-dimensional form of carbon is graphite, and we know it for a good 500 years, and I'll come later to this to this date. And then for about 500 years, there wasn't, well, for 400 years, nothing much was happening. And then about 30 years ago, so-called the zero-dimensional form of carbon, the buckyballs or cage molecules have been discovered. And then about 10 years later, quasi-one-dimensional form carbon nanotubes have been obtained. Now there is obviously a gap at the dimensionality 2, which theorists filled in quite readily. They introduced this fictitious material called graphene, but it has never been obtained until recently. And then the situation is quite bizarre, because if I ask you which one of those materials is studied theoretically the most, graphite, which we know for good 500 years, buckyballs or carbon nanotubes, which we know for 20, 30 years, or graphene, which is the newest member of the family. Well, it's of course graphene which is studied theoretically the most, because it's the simplest possible form, just flat arrangement of carbon atoms, hexagonal lattice, and theorists don't like complicated problems, so they would solve this very simple problem on the hexagonal lattice, and they say that cage molecules is just wrapped graphene, and carbon nanotubes just rolled graphene, and graphite just graphene layers stuck one upon each other. And but it was left as a fictitious material for quite a long time, until, well, we managed to isolate it in a free form. And so the rest of my talk will be organized in 2 chapters. You probably already noticed that I stole the title of my talk from the famous book of Edwin Abbott. And as the book itself, I will have two parts. First is this world, the two-dimensional world in this book, and then we will try to make a connection to the three-dimensional world later. So why two-dimensionality is so important? Well, it's because it's very hard to obtain two-dimensional crystals. So here is a model of 400 carbon atoms playing with each other at elevated temperatures. And sometimes they look like they're forming flat structures, but in fact, if you allow them to play for much longer, they will always come into some three-dimensional arrangement. And there are many reasons behind that, like surface tension and the termination of the dangling bonds and so on, but there is one very fundamental, is that two-dimensional crystals or two-dimensional structures are not stable at any finite temperature. So it's a so-called Merwin-Wagner theorem. So how can we overcome this problem? And the critical problem here is the temperature, because usually when we grow any crystals, we use elevated temperatures, and then if you try to do it with two-dimensional crystals, they will always roll up or maybe even decompose. So how can we overcome this problem that all the crystals around us, or all the objects around us, are actually three-dimensional? So that's probably the largest two-dimensional object which has been which was available to us prior to graphene, 222 carbon atoms. Well, the solution is quite simple. You have to start with this three-dimensional object. So you grow this three-dimensional object like graphite at high temperature, and then you use low temperature and try to exfoliate it and slice it into individual planes. And it's known that graphite is quite easy to slice into quite thin platelets. So those are the SEM images of those, but you do it at home every time you use a pencil, because when you draw a line on a paper with a pencil, what you do, you exfoliate graphite, you leave a trace of exfoliated graphitic particles. However, what you need is quite thick particles, because you want to see what you're writing, though there are quite a few of those which are quite thin, which you don't see, and that's exactly is of interest for us, because the idea is, can we try to isolate and slice it into up to the model layer? Quite a few people tried it, and so here is pencil trace on a special substrate under a microscope. So the purple color is the substrate. It's silicon oxide, and the graphitic particles of different thicknesses can be seen as different colors. Those whitish are the thickest ones, and then the light blue and then blue and purple are the more darker purple it becomes, the thinner it is, and those which you practically cannot see, those are exactly the monolayers. Well, at first it took us quite a bit of searching through those crystals. However, because our first samples were quite small, just about a micrometer large, but it's already enough for our nanotechnology fabrication technique to produce certain meaningful devices out of it. But our days were quite good at our scribbling, and we can exfoliate millimeter-sized crystals without any problems. So immediately after people isolated it, we jumped into the research of those crystals, and quite a number of very interesting and very unique properties have been discovered. Of course, it's the thinnest possible material, is the strongest, the most conductive, the most thermally conductive, the most impermeable, the most elastic, and so on and so on. And as I usually say, the most important property in this list are those three dots, because we come across the new interesting properties and come with new ideas quite often, basically on the monthly basis. Let me now try to pinpoint where all those properties are coming from, and I'll especially talk about the electronic properties of this material. And you would have to be with me for a couple of slides. So if you manage within the next 2 slides, then you would manage through the rest of the lecture easily. So all those properties are really coming from the hexagonal symmetry which we have for carbon atoms in graphene. The hexagonal arrangement of carbon atoms, it looks extremely simple, but in fact it's not the simplest possible. It's not one of the 6 simple Bravais lattices, because you cannot take one atom and replicate this hexagonal structure. You always need 2. So I colored them differently, the red and the green. Of course, in reality, they are not colored, but you can always distinguish between them. Say all the red would have a neighbor from the bottom, and all the green would have a neighbor from the top. And because we have 2 atoms per unit cell, so we always have to play with combinations of two electrons which are living on those two sides, on the green and on the red side. And because we have to play with those two, we create two energy bands which are crossing at two very special points of the Fermi surface, and this gives us the linear dispersion relation for our quasi-particles. Let me summarize what is so special, why this linear dispersion relation is so special. Generally, all the materials which we are used to have, or the electrons there can be described by Schrödinger equation, and there is momentum and there is mass in this equation. And all those materials can be divided into two large parts. One, those metals or semiconductors where electrons conduct electricity, or those where holes conduct electricity. So the p-type, so the n-type and the p-type. To make a connection to real world, it's like having a country with single party system. So you are free to move within this country. That's how you move within either p-type or n-type semiconductor. But then when you try to connect the two, you create a barrier. So you try to connect the two countries, you would have a border control, because it's impossible to convert one into another. There is always a band gap, and there is always a border control. So in brief, in two sentences, that's how modern electronics work. You need two countries or two materials with different types of carriers there, electrons and holes. You connect them, and you can control your current. In graphene, the situation is very different, because we have linear dispersion relation. We don't have mass in the equation. There is only momentum. So we have massless particles. So that's the situation which people are used to in high energy physics, for example. And it means that there is a certain symmetry between your electrons and holes, or it's so-called chiral symmetry, or if we talk in the language of relativistic physics, is the symmetry between particles and antiparticles. They're basically described by the same equation and by the same wave function. So if I need to create similar example for graphene, I would have to use United States, where you might have one state to be Republican, another one is democratic, but you can always go from one state to another without any problems on the border control, because you can always convert from electrons to holes, and because there is no band gap. Just to make the situation even worse, we can play with new generation of those exotic particles. We can create massive chiral fermion. I don't think that those exist in relativistic physics, and I don't have a country to represent those, so I won't go into details on that. So, and this very special linear dispersion relation also guarantees us that we have very special electronic properties, because those electrons, they can be converted into holes and back quite easily. They don't scatter as much as the regular as the electrons in any other materials. So the figure of merit for the amount of scattering, the mobility, which shows you how fast electrons travel through the crystal, is extremely high there. So at room temperature is about 1/4 At low temperature is a few millions. And just to give you something to compare, this number for silicon is about 1,000, and in the best hemmed transistors, which are in your mobile phones, it's about 50,000. So graphene is doing reasonably well on this scale. There are problems. The there are problems with it that because those electrons are massless, we cannot stop them. We cannot create a barrier which would stop those electrons, and that's to rephrase it in the language of relativistic physics is so-called the Klein paradox, and that gives us a little bit of a headache when we try to create a transistor for logic applications, but people are working on this. But let me probably skip this. So optical properties are quite interesting. Optical properties of graphene are quite interesting and unique as well. You might ask what kind of optical properties you can get. It's only one atom thick. Say we have millions of atoms between me and you, and I can see you easily. What would an extra layer of atoms would do? Well, it's quite it's surprising, but it absorbs quite a large fraction of light, namely 2.3%. So this picture is a real optical picture of graphene. So there is graphene here. There is nothing, just a void, and there are two layers of graphene. And I guess I hope you can see slight contrast there. So this contrast is about 2.3%. So one layer of atoms absorb quite a sizable fraction of light. Even more interestingly, this 2.3% is not just a number. It's actually given by a combination of the most fundamental constants. It's pi times alpha. Alpha is the fine structure constant. So do it at home. 3.14 divided by 137, you get 2.3%. So and it doesn't depend on any material parameter. Wherever in the world you prepare graphene, it absorbs always the same amount of light. So what you do, you pick up a piece of graphene, look through it, and the contrast which you see gives you the most fundamental constant of this universe. Now, 2.3% is, of course, quite a large number for physicists. We can measure it quite easily. However, it's extremely low number for device engineers. They would kill to have a material which absorbs only 2.3% of light and would be as conductive as graphene, because it would be in the heart of any application, any device which would require transparent and conductive coating, like LCD display or touch screens or solar cells and so on. And here we created an LCD, well, 1 pixel of an LCD display where graphene has been used as a transparent conductive coating to replace ITO, and it does work. You can pinch off the optical transmission quite easily, and here we benefit from its high transparency, high conductivity, but also from the fact that it's inert and also flexible material, so it can be used for future devices. And this basically brings us to the applications that in principle they are quite realistic, but before I go to the applications which will be, before promising you some future applications, let me show you what graphene has done for us already, because I try to demonstrate it, or to always demonstrate it. So one thing it did already, it created workplaces. Say a year ago, I would say not many. We had 3 spin-offs from our university. There are a few from others, so it wasn't much. However, this year, the number of companies which produce graphene, sell graphene, or use graphene in some applications grew quite dramatically. So it's not. It was meant as a joke a couple of years ago. It's not a joke anymore, and especially it's not a joke because about a year ago I received my regular copy of the Glamour magazine, and then on one of the pages you find five jobs our kids will be doing, and then right next to virtual architect, avatar stylist, active makeup developer, there is graphene engineer. And if stated by Glamour, it should be true. Then it also provides entertainment. I guess many of you follow the Big Bang Theory. It's, for those who don't, it's a sitcom. It's the American sitcom. It's about 4 postdocs in Caltech, and one of the major characters is Sheldon, the string theorist. And in one of the episodes, he was trying to resolve the question why electrons in graphene move as quasi-relativistic particles. You all know this now, but it took him the whole episode long to realize why is it so, and it's not a surprise because some of the formulas they are actually wrong. So it's not they're not for monolayer graphene, they are for bilayer graphene, which we didn't discuss. It also gives shelter if you fancy to move to Tallahassee, Florida. You can quite as well live on the graphene lane. So the houses are so there, but it's a new lane. It just started. So realistically, well, it has a number. There are opportunities for number of applications. I'll just give you another one which is being used already. So that's the use of graphene as a support to study biomolecules in transmission electron microscopy, because what you need there is a support which you won't notice, so it's extremely thin, but at the same time it should be conductive and mechanically strong and transparent for electrons, and if possible it will be regular, so you would be able to filter out the diffraction peaks from your support. And that's all graphene. And here is an example how we used it to look at in this case, tobacco mosaic virus, and you can see the virus quite easily, so without any staining. So, and it's a product from several companies. That's actually generally, I think, although many applications are being focused on electronic properties and the optical properties, my personal feeling is that the life science applications are going to be larger than those. Just to give you one example, is the DNA sequencing through pores in graphene. Several groups demonstrated it. I thought that, well, it's a nice idea for a research lab, but I'm not sure if it can be taken forward. Apparently, there are companies now who are pushing this idea forward, and they're actively developing it. And generally, the healthcare, there are a number of areas where graphene can be used in the healthcare, like in the artificial organs, like in artificial eye or artificial skin. That's the membranes and sensors. Lots of applications on the sensor side or on drug delivery side. So generally, the applications on the bio side are probably going to dominate in the next 5-10 years. So lots of applications are realistic. We spoke about the touch screen, the LCD display, the solar cells, the tactile display, which is one of my favorite. People in Cambridge are developing it, and it's a funny application, but it will probably go through because what is good about everybody nowadays are using those smartphones, and they are always good apart when you are on a lecture like this, because when the lecture is boring, on the old phone you could feel the buttons and you could text and do your work at the same time looking straight into my eyes. With these phones you cannot do it because you have to look at your phone. So tactile display sends high frequency. Well, it's not actually very high, just AC signal to the buttons, so you actually can feel the buttons on your smartphone, and you can use it on the lectures like this, just looking, still looking into my eyes. In electronics, lots of applications in sensors and transistors, composite materials and energy like supercapacitors and barriers. And batteries So those are all being developed as we speak. Now, however, you probably have already noticed what is the potential problem there, because those applications are, of course, realistic, but do we have that amount of graphene available? I showed you this single pixel for the LCD display, and that was 30 micron in size. And of course, for your lounge, you want not 30 microns, but 30-inch display. So what is the state of the mass production of this material at the moment? Before we go to the mass production of graphene, let me talk a little bit about the mass production of graphite, because I simply love this story, and it has some connections with Manchester, with the Northwest in general. So graphite has been obtained for the first time in a place called Seathwaite in the Borrowdale Valley, close to Keswick. And this date, 1564, is when two royal commissioners traveled there, and they applied the Royal Commission for the use of those mines. They didn't know how to use graphite at that time, but it was already taxed, as usual. So you still can go there, and those mines are still preserved for extremely nice inside. You still can collect some of the graphite, and then surprisingly, it made its way across Europe quite fast, because the next mention of graphite we find in the book of Konrad Gerstner, 1565, published in the year of his death, and where he already described the first pencil. We actually know that he never seen this pencil. He used the correspondence with his German friend to get this picture. So it shows that the English graphite made its way across Europe extremely fast. Now the owners of those mines, they were extremely fast in recognizing the strategic importance of this material. So they inflated the prices artificially by closing the mines for most of the time and opening it only once every 7 years, roughly. So the prices indeed went extremely high, and at certain moment, a pound of graphite was £1 and £1 at that time was quite a large amount of money. Say it would be a weekly wage for the workers who worked in those mines. So the problem with stealing and unauthorized access to those mines was extremely severe. So the owners even pushed for a special legislation through the parliament, which dealt specifically with the stealing and unauthorized access to those mines. And the punishment for that was public whipping and a year of hard labor. And I still remind to every student in our lab that this legislation is still true. If you touch graphene, you're condemned for 3 years of hard labor as a PhD student, and then public whipping at your viva. So now the very title of this slide, the black market, actually comes, or as they claim in the Keswick Museum of Pencil, it comes from the illegal market of graphite, which existed in 17th, 18th century Britain. I'm not sure how true is it, but it's not my theory. So nowadays there is a reasonably legal market of graphene. There are a few companies. Actually, quite a few companies there already. One of the first one was a company opened by our students, the Graphene Industries, and they started with selling graphene at some ridiculous price of £1 per square micron. Easy to remember. I'm not sure how much justifiable it is. And it was okay for the very beginning, because our original samples were extremely small, so they barely could afford the postal expenses. However, as the sizes of the crystals went higher and higher, you can try to extrapolate the price, and then one sample would worth you a million. And so I always tell to the owners that their business is not really sustainable, but apparently they still work. But luckily nowadays there are several other means how to create graphene. So the mechanical exfoliation of a pencil is one method, which is the preferable method for most of the experimentalists in the world. However, there are Cvd graphene, which allows you to grow extremely large areas. So you can buy, I don't know, 10-meter long roll of graphene easily, and there is a company which produces 300 square meters of graphene a day. So that's not an issue. There are a few other methods like epitaxial growth on silicon carbide, and for low-tech applications, there is always chemical exfoliation, either directly or through the graphene oxide. But now, before we go, I'm not going to go much into details on those. It's a reasonably established technology, and people are making it cheaper and cheaper. And now it's extremely robust and viable technology. I want to go now to a little bit of beyond graphene. So obviously, with the announcement of this National Graphene Institute, our students who are always active and bright eyes, bushy tails, they always ask for more, and they keep asking, so now we have all those money, can we buy some equipment probably, and rather than buying just the lead pencil, can we buy the whole set of the pencils and try to exfoliate other materials as well? And in principle, it does work. You can create two-dimensional crystals out of other materials as well. The most used nowadays are boron nitrides, molybdenum disulfide, tungsten disulfide, some complex oxides. And apparently, it's what you can do. You basically create a whole family of two-dimensional crystals. All of them are just one atom thick, but they are quite stable, and their properties quite often are very different from the properties of the three-dimensional precursors of their parent material. So pretty much all of them are worthwhile to investigate and to study, and there are lots of groups in the world who do those investigations. There is another way how to produce new two-dimensional crystals, is to think about is to think about graphene as a large scaffolding and as a large aromatic molecule, which is suitable for chemical modification, and then you can run various chemistry on it, like you can attach fluorine atoms on top of it, and you basically get fluorographene, or two-dimensional Teflon if you want, or you can attach hydrogen and you get so-called graphene, and both materials quite stable, and both materials are very different from graphene itself, but apparently you can attach pretty much anything. So carbon is extremely reactive material, of course, extremely reactive atom. So you can attach, and the fourth electron there is free, so you can use it for your chemistry. So now we are getting to the second part, which will be shorter, to the second part of my talk, same as in the book itself, from the two-dimensional world to the three-dimensional world. So we have this, and just let me give you a little bit of an introduction for this part. If you think about it, only few materials really determine our worlds. For electronics, it's all silicon, of course. For construction engineering, it's mainly steel. For aerospace engineering, it's aluminum, a little bit of titanium. And we learned to live with it, but it limits the opportunities quite severely, because before developing any application, what an engineer should do is to consult a textbook and look what silicon can do for me, what kind of band gap, what kind of doping can I get, and then you are allowed to construct your new application based on those parameters. We learn to live with it. We simply don't notice it, but it is there. Instead, if you won't be limited by those constraints, you'll be able to create new applications. So, and those do exist already. You try to combine different materials together, and that's the subject for composite materials and heterostructures. And that is extremely successful area because, say, lots of lasers are coming this way. The hemmed transistors are coming this way. Composite materials and plastics is basically a result of mixing several materials, the properties of several materials together. Carbon fibers being used in airspace engineering, of course. So it does exist already, but it is only limited. Those only limited examples. What would be really nice if you start with the application, think what kind of material what kind of properties do you need, and then you design a material for your applications, really ideally just starting atom by atom. So you would be able to design with extremely high precision any properties into this material and any functionality you want. Say you want the top layer to act as a sensor, the next one as a solar cell to provide power, the next one as a transistor, the next one as a support layer or conductive layer, and so on. And with the appearance of this family of the two-dimensional crystals, in principle, we do have this opportunity, we do have this platform, because what we can do, we can now, if we have a library and a catalog of those materials, we just start with the application and we try to combine individual crystals, but then in random order, or in the order which we want, to create a new material, a new three-dimensional crystal, which doesn't exist in nature, but which we can design and create in the lab. And it would be, we can do it with really high precision, or with the atomic precision, basically, and it would give us the functionality which we want. So we can quite easily design this to be a transistor, and so that's actually is a transistor, believe me, and that's as a solar cell, and then that's as something else, and it's not science fiction. So that's those are the examples of the structures which we already created and which do work as transistor or solar cell or even LED, or as an LED. Well, and there are quite a number of the materials which are available to us, and we use and we produce different transistors, for example, with different parameters from this technology. Unfortunately, of course, nowadays it's all in the lab. We have to do it manually. We take one layer of atom and put it manually on top of another one, and then put another one and put another one. So it's quite an elaborate process, but our students are getting extremely good at it. But you pay this high price for the level of flexibility, and you can basically put contacts anywhere, and you can address every single layer of atoms. So it's a new level of flexibility. Oops, sorry. Now we're getting. It's probably easier to go this way. So it's a new level of flexibility, and because the range of the properties of those materials is extremely large, and the number of those materials is large as well. So we can create the heterostructures which are extremely rich and multifunctional as well. So I wanted to give you two examples. One is how good are those heterostructures. You would think that if you create something by hands, and the hands are always dirty, so what kind of quality can you get? So here is an example of one of our heterostructures. So we took an actual device. So that's how it looked like. It's a specific device used for the study of drug. I'm not going to go into it, but what we did, we cut out a small piece out of it, an extremely thin piece, and we took it out and we used it, we put it into a transmission electron microscope, and you can see in transmission all the layers there. And so what you see is the underlying boron nitride, then there is a layer of graphene, then there is another layer of boron nitride, and then there is graphene as well. And you can see that the periodicity is there. And here is another example. Here, what we started with boron nitride, which is a layered material as well. Then we put 2 layers of graphene on top. Then we put 2 layers of boron nitride, and 2 layers of graphene, then 2 layers of boron nitride, and then 2 layers of graphene. Yet it's not just for the sake of to impress anybody. It's an actual device. We studied tunneling, resonant tunneling through this barrier with a quantum well inside. But if you look at the dark field image of this, you won't notice where the underlying boron nitride stops and the layer of the heterostructure of graphene and boron nitride starts. So the periodicity is practically unpitched up. So the quality of those heterostructures is extremely high. Just to give you an example that the variety of the materials which we can use is quite large as well. We also produce tunneling, so-called tunneling transistors made from very unconventional material. Traditionally, people use boron nitride, tungsten sulfide, but in principle, you're not limited by anything as long as it is reasonably high quality material, quite thin, can be exfoliated into monolayers, and there are no defect. And for example, we can use clay thermoculides. And one of the reasons why we decided to use this for our transistors, because you can buy it in any convenience shop. It's basically the main ingredient of your cat litter boxes. The only trick is to use it before it's been in the boxes, so not after. And then it actually the transistors which we can produce from those materials do work. It, of course, also gives us extremely rich physics there. I mean, just to name a few, the fractional quantum Hall effect, drag, the so-called Hofstadter butterfly on the Marat pattern between graphene and boron nitride. So there are quite a few extremely exciting physical experiments which have been produced already on quite simple heterostructures, and those heterostructures are getting more and more complicated every day. And in terms of applications, they're quite we're working on the future devices, because we tried to produce some time ago. We tried to produce a timeline for future applications. And we offered a logic transistor somewhere in 2030, 2025. And so those transistors are quite likely to be based on those heterostructures. But we need a little bit of time, of course, to develop those. There are quite a number of other applications for graphene in telecommunications. Now, I'm not going to go into all those applications. Just let me say a couple of words how realistic are those timelines. So when we were trying to predict the future a couple of years ago, we published it. Of course, we were quite anxious because we had to, just how things have been developing, we had to predict that the first applications should be coming out already 2013, 2014, so basically now, and we're quite anxiously waiting for for this year and the next year. Can we see any actual applications on the market? And my favorite line about those predictions are by Arthur Clarke, which basically says that if we learned one thing from the history of invention and discovery, that in the long run and often in the short one, the most daring prophecies seem laughably conservative. So we were quite anxious for this year, where the touchscreen displays should appear on the market, and we were quite lucky that there is one company, US/Chinese company, which now produce touch panels made of graphene, and then they don't only produce it, but they actually sell it. They sell, according to them, they sell 2 million per month, but only in China. So there is quite a good chance that if you buy a phone in a small shop in China, it would have a touchscreen made of graphene. So just let me finish that the work which we do, for example, on those transistors, so it looks extremely academic, but we are quite proud that large companies are following our footsteps. So Samsung followed our footstep on those transistors, which basically give us the insurance that the physics which we do and the technology which we develop will be one day used in the real life applications. And let me finish with this, just put a few conclusions here, but the most important slide is to thank all my collaborators. There is a big group of people who are actively working day and night on those developments, and I'm really grateful for their support and their collaboration. Thank you so much.